Our last two sections, I guess, the last group of sections here in chapter 5, rational graphing rational functions. We're going to do some more with graphing, and the fundamental theorem of algebra. We're actually going to start with that, the fundamental theorem of algebra. The last video we did was all about using division to solve higher or higher degree polynomials. We use synthetic division as a shortcut, but you can certainly use long division. There's nothing wrong with long division. It's just a little bit longer. And we're going to use that same idea. We're just going to take it one step further. And this is as far as we're going to go with it. So at the very end of the last video, I gave you a third degree polynomial and said, solve for x if it equals 0. And I gave you one of the solutions. I said x equals 1 or x equals 3 or something. Now we're going to figure out where that came from, where that one solution came from. So we're going to start with just a third degree polynomial or a fourth degree polynomial, and that's it, and say solve. And so we're going to have to figure out how to get that initial thing going. And that's where we're going to pull a few different theorems in here. So let's look at the fundamental theorem of algebra. It sounds like it should be really like deep and difficult, but it seems to make sense. It is intuitive. This is what it says. If you have some degree polynomial, an nth degree polynomial, fourth degree, fifth degree, so whatever the highest exponent is, and if you set that polynomial equal to 0, so p of x equals 0, you will be able to solve for exactly n solutions. So let's think about our quadratic equations. That would be a second degree polynomial because x squared is the biggest exponent. It has 2 solutions. There you go. If you have a third degree polynomial, a cubic equation, or equals 0, you'll get exactly 3 solutions. A fourth degree, or quartic, so x to the 4th power, 4 solutions. So whatever the biggest exponent is, that's how many answers you're going to get, which seems to work. It jives with the way we think. It does say here that all the solutions will be complex numbers, and that might take you a second to figure out a contradiction, that when you've solved for x, sometimes you get like 2, x equals 2, and that's a real number. But this says all the solutions will be complex numbers. One thing to remember is that any real number can be written as a complex number. 2, for instance, could be written as 2 plus 0i. Complex numbers are a real part and a complex, or an imaginary part. That's what makes it a complex number. So if you have a real number 2, it has 2 real parts and 0 imaginary parts. So when it says all solutions will be complex numbers, they don't mean that all of them will have an imaginary part. It just means that you can write them all as a complex number. So imaginary numbers and real numbers both work together here. It does say some of them will be, some of them may also be real numbers. There you go. I remember that real numbers are subset. There you go. Okay. There's 3 ways that you can kind of see this. I'm going to give you some graphs here. One way is this way. So this is a quartic equation, a 4th degree polynomial. You'll notice it never crosses the x-axis, which means that it has no real solutions or strictly real solutions. But it does have 4 complex solutions. And if you imagine a little dashed line right here, so if we moved this w down, so it did cross the x-axis, it would have 4 different solutions. 1, 2, 3, 4. It just happens that these 4 solutions are complex. They're imaginary, completely imaginary numbers. There's no real part to them. I take that back. There might be a real part, but they're definitely complex. So it could be that they're all complex solutions. It could be that they're all real solutions. This is a third degree polynomial, a cubic polynomial. It crosses the x-axis once, twice, 3 times, and this can have 3 real solutions. There's one other way that it could happen, and this is what it says right here, some of which may be repeated solutions. What that means, or how that would look, is like this. This doesn't cross the x-axis twice. It only hits it once. It's a tangent line, just barely touches it. And it doesn't have any complex solutions, so it appears to only have one solution. However, if you were to write this equation out, remember that using the vertex form of this parabola, it'd be like x minus 2, because it moves over 2 within the parentheses, so x minus 2 squared, which expands out to this. And so this is going to have two different solutions. X could be 2 or x could be 2. We have a repeated solution. So this polynomial here, this quadratic equation, does have two solutions. It just happens that it's the exact same solution. It could be 2 or it could be 2. And that's what this would look like. Okay. So that's, we've got our solutions there then. Repeated solutions. All right, we're going to look at this theorem here, and this one is almost as complex as it appears, I'm sorry to say. So what this says, I'm going to try and walk you through it very slowly. What this says is, if there is a solution to a polynomial equation, and that solution is rational, so there's always going to be an answer. There's going to be n answers to an nth degree polynomial. That's what the fundamental theorem of algebra just told us. But if the answer is going to be a rational number, which means it's in the form of a fraction or really a whole number, it could be like 5 over 1. And so if it's a rational number in lowest terms, so reduced, if this rational number is a solution to this polynomial, then p, the numerator here, p is a factor of the constant term a sub 0. So p, this numerator in our potential hopeful solution, is some factor of this number here. And q, the denominator of this fraction, is some factor of the leading coefficient at the beginning. So if we're going to find a rational solution, if there exists a rational solution to this problem, it's going to be in this form. We have all the factors of the end coefficient, the constant, over all the factors of the leading coefficient. Here's an example. So I've got this cubic equation. I want to be able to solve this. I want to solve it for 0. I want to figure out what x is. What this theorem says, the rational solutions theorem says, if we're going to find a rational number as the solution, we're going to have to look at all the factors of this constant. So the factors, remember, are numbers that multiply together to make 6. So like 1 and 6, 2 and 3. I think that's it. So that would be all our different factors of 6. And that's the numerator. The denominator, q, is going to be all the factors of this leading coefficient, so 2 in this case. All the factors of 2 are 1 or 2. So it's either going to be 6 over 2, 3 over 2, 2 over 2, 1 over 2. These are all potentials, or 6 over 1, 3 over 1, 2 over 1, and 1 over 1. There are 4 different factors of 6, and there are 2 different factors of 2. So these are all the different possible answers that we could get. And it's a cubic equation, so there's only 3 answers. There's exactly 3 answers. We have 8 choices here. One thing that you may notice is that some of them are repeated. 2 over 2 is the same as 1 over 1. So it does say in lowest terms. 6 over 2 is the same as 3 over 1. And so there are some repeats in this. So really, these are our different possible answers. There's 1/2, 1, 3/2, 2, 3, and 6. However, there's another piece to this. So we have narrowed down these 8 down to 6 possible answers, and there's only 3 of them that are the actual answers. But 6 could be 3 times 2. It could also be -3 times -2. So all of these have to be considered that the negative is also a possibility. -6 times -1 is also another set of factors for this. So really, we have 12 possible solutions. We have plus or minus a half, plus or minus 1, plus or minus 3, plus or minus 2, and so on. That's a lot of potential answers. Luckily, there is one thing we can do to speed up the process. We're going to have to do some guess and check. There's no way around it. You're going to have to do some guess and check. And the one saving grace that we have is if we want to know if one of these is a potential solution, that means that when we plug that number back into the equation, we should get 0. I'm going to say that again. There was a theorem in the last video in section 4, I think it was, that said if P of R, if we plug some solution that we want into the original expression, the original polynomial, if that equals 0, then the remainder is 0. So if we plug that number in to this polynomial, whatever we get that comes out will be the remainder. And since we want this to be a solution, we want it to be a factor, we want it to have a remainder of 0. So if you want to know, is 1 a solution, or is 2 a solution, or is 3 a solution, plug it into the polynomial. If it equals 0, then the remainder is 0. And that means it's going to be a factor of this polynomial. And we need that to happen. We need to know at least one of the solutions. So let's try that. I'm going to try 2 to start with. I'm going to avoid the fractions for now, simply because. And so I'm going to try 2 to the third power. Be careful with parentheses, especially if you get into negatives, because -2 squared will need to have an extra set of parentheses when you're using a calculator. Times 2 plus 6, okay, equals 0. Hey, wow, good guess. 2 is a solution. So that happened to work for me. It may not be your first try. We had 12 options. I could have tried 6, I guess. That wouldn't have worked. I happened to put in 2 and it worked, which is great. So I'm going to move over to my document camera here. Now I know one of the solutions to this equation. I know that one of the solutions is 2. Which means I should be able to do, I'm going to use synthetic division. I should be able to say that 2 is a solution. I'm going to put all the coefficients here for synthetic division. So I just wrote down all the coefficients. And I'm going to pull the first one down. 2 times 2 is 4. If I add these together, I get 1. 2 times 1 is 2. Now I should get a remainder of 0 because I followed my theorems. -5 plus 2 is -3. Good, because 2 times -3 is -6, which has a 0. I have 0 remainder. 2 is a factor. I'm left with then 2x squared plus x minus 3. And I factored out. Remember, just because it's a 2 doesn't mean the solution over here is a plus 2. The way the theorems were set up, whatever my solution is going to be -2. And a big part of that is that if you set this equal to 0, x minus 2 equals 0. If you use that product rule, x would have to be 2. 2 minus 2 is 0. So the solution is 2. We write -2 because 2 minus 2 would give us the 0. Okay, so I've got one of the solutions. I factored that out. Now I have a quadratic. I could do synthetic division again. I could do the same thing. However, I'm going to try and factor this. So I want to try and find, maybe I won't. I could. I'm going to use the quadratic formula just because it's early and I'm tired. So I'm going to do ABC. I'm going to do the opposite of B, plus or minus the square root of B squared, minus 4 times A times C, all over 2A. So I'm using that quadratic formula. 4 times 2 is 8 times -3 is going to give me -24. So I'm going to have 1 plus 24 is 25. So this will give me some real solutions. That's nice. 5 all over 4. Square root of 25 is 5. So I've got -1 plus or minus 5 all over 4. So -1 plus 5 is 4. Divided by 4 is 1. So x could equal 1. And -1 minus 5 is -6. Divided by 4, -6/4 is -3/2. And just to reference back here, so we got our solutions. The solutions were that x could be 2. That was our solution right here. X could be 2. X could be 1. X could be -3/2. And like I said, just to throw some reference in here, these were our potential solutions. 2 was a solution. 1 was a solution. There's that 3/2. and it could have been negative. Negative 3/2 was the plus or minus. So those three solutions did show up right here. I'm glad I didn't try a half. That wouldn't have worked for me. And that's where they were. Let's do another example. Let's look at this one. Yep. Again, find all the solutions to this cubic equation, x cubed minus 3x squared plus x minus 3 equals 0. So if we use the same rational solutions theorem, we're looking at all the factors of the constant. So all the factors of 3, doesn't really matter if it's a negative 3 because we're going to do plus or minus either way. So all the factors of 3, it's 3 or 1. Well, that narrows down our solutions. That's pretty good. The leading coefficient is 1. Well, that works out really nicely too because there's only one factor of 1. That's 1. So really our only potential solutions are 3 or 1 or negative 3 and negative 1. So we got plus or minus 3, plus or minus 1. Those are the only possible answers. There's only 4. This is a cubic solution or equation, which means if we're going to find a rational solution, if there's going to be a solution that could be written as a fraction, it's going to be one of these 4. Pull up that calculator again. So I'm going to use the theorem that says if I plug these numbers in to that original polynomial, whatever my remainder, whatever it equals is the remainder, and I want the remainder to be 0. Let's try 3. So if I do 3 cubed minus 3 plus 3 minus 3, get 0. All right, good guess again. So I've got one of the solutions. One of the solutions is 3. I could try more, but I'm gonna go with 3 for now. I'm gonna go over to my document camera again. So here we have the original polynomial. I know that one of the solutions is 3. So I'm going to use my synthetic division again. I've got 1x cubed, negative 3, 1, and negative 3. So I'm going to pull that first one down. 3 times 1 is 3. Add these together, I get 0. 3 times 0 is 0. Add these together, I get 1. 3 times 1 is 3. Add these together, I get 0. So there's my remainder of 0. So x minus 3. And I've got x squared plus 0x. So I'm not even going to write it. Plus 0x plus 1 equals 0. Again, the solution was 3. So 3 minus 3 is 0. That works out. It has to be that minus 3 because this was a positive 3 there to give me that solution. X squared plus 1. I guess I don't really need to factor that. I can just set x squared plus 1 equal to 0. If I solve, I get x squared equals negative 1. And I take the square root of both sides. Get plus or minus the square root of negative 1. Square root of negative 1, that's imaginary. In fact, we have a special name for that. X could equal plus or minus I. One thing to be careful of, if you were looking for a shortcut, like how can I avoid doing work and get the right answer either way? Just plugging in those numbers, plus or minus 3, plus or minus 1, wouldn't have gotten you too far. 3 is the only rational solution. Now, I will give you problems that have at least one rational solution. I'm not going to give you a problem where there are no rational solutions. You will get at least one rational solution in the problems that we're doing. But it may not be all of that. All the solutions may not be rational. So simply plugging in the numbers and seeing which one give you 0 may not be the best way to do it. Find one, do the synthetic division, and then or long division, factor that out, and then go from there, because you might get some imaginary answers. So the answers for this one were 3i and negative I. Those were all the different solutions to this cubic equation. Those are the answers there, plus or minus I. This is what it would look like. So when you graph it, it looks like this. You'll see that it does cross the x-axis at 3, so that's where that rational solution came from. But that's the only place that it crosses the x-axis. And so the other roots are going to be complex. They're going to be imaginary. They're going to be I and negative I. All right, I'm going to stop there for this video. That's section 5.6 on a fundamental theorem of algebra. We're going to use that again in a project for this chapter as well that I'll do in a follow-up video.